Okay, so I want to okay, so what I want to talk about is you know, some you know, there's been some recent work on area laws and complexity of quantum states, and I want to try to put it all together and you know, sort of illustrate the main ideas behind it. Okay, so we all know that quantum systems are exponentially powerful. Okay, so there's no, is there a pointer or
there's a little red button.
yeah, okay, yeah, is there something else I should be doing as well, or
I have another one if you want to use this.
Maybe I'll oh, okay, shall I try plugging in this one?
Oh, that's yours?
Yeah.
Oh.
So let me.
Yeah, then it should work.
So
Sorry, just plug yours in.
yeah. Okay. So let's see if. Okay, let's see if that works. No. Okay. We have a pointer that works, but now. So why is it not identifying?
You want to try mine?
Sure, maybe. Let's see. Maybe we just have to restart or something.
Worked last week. So here's
Okay, good. No, we are working.
Right?
Yeah, yeah. Okay. Okay, so so of course the field of quantum computation asks, well, how does this change computation? And quantum Hamiltonian complexity asks, what are the implications for physics? Now, okay, and naively you can ask, well, if quantum states have exponential description, how can we do physics? And
we or nature?
we, people. And of course, you could also ask how nature does it, but we'll be a little more modest here. And so, one way you can pose this question is by asking, you know, could it be that there are natural classes of quantum systems which do not suffer from this exponential complexity, right? So are there natural states which sit in a tiny corner of Hilbert space? And so, if you talk to condensed matter physicists, they would say, well, low temperature, you know, at low temperatures things are somewhat simple, that you can, you know, if you look at ground and low-lying excited states, you can understand those states. Now, what in quantum Hamiltonian complexity, you know, this kind of intuition is sharpened and formalized in the following way. So to formalize this intuition, the questions we ask are, is there a compact description of such states? Moreover, what that means is polynomial size description in such a way that the interesting properties of such states can be computed efficiently, meaning in polynomial time. And then further, you know, we'd like to ask, in fact, can we go even further and compute such compact descriptions efficiently, right? So efficiently, again, polynomial time. So this is sort of a, you know, a formalization, if you want, an attempt to formalize this kind of intuition. Okay, so let's see what kind of states we are interested in. You know, so if these were classical states, we'd be, you know, spins plus minus 1 with some kind of interactions. Then the energy would be given as summation over all edges ij of this interaction strength times sigma I sigma j. Right? This would be the classical picture of what the energy of such a configuration is, where the sigma i's are the configurations of each spin. Now, if you work with a quantum system, quantum many-body system, again you'd have either spins or let's say each particle is instead of being a it could be a d-state system. So now your Hamiltonian is a sum of terms as before, a sum of terms corresponding to each interaction. And for each interaction, instead of describing it as a function of those two spins, you now describe the interaction as a Hermitian matrix, right? So because it can assign an energy penalty in any basis of its choice, right? That's oh, okay. So what was sigma here? Sigma was the value of So imagine that these circles here represent your particles, which are, let's say, spins. So they are either +1 or -1, right? And so you have a configuration of spins. That's the state of your system. And now you want to know what's the energy. Well, the energy depends upon some function, which says what kind of interactions you have. Are they ferromagnetic or antiferromagnetic? Okay, so that's the classical picture. And now, I'm just showing you what the quantum picture looks like. So now in the quantum picture, let's say instead of spins, you now have qubits, right? And your qubit can be, instead of classical spins, they'd be quantum spins or qubits. And now your qubit is a vector in a two-dimensional vector space. And so now to describe the energy, you must say for any value of this, any state of this qubit and any state of this qubit, what's the energy penalty? And that's described by a Hermitian matrix that that describes what that energy penalty is. And in general, if instead of a qubit, this is a d-state system, so it's a superposition of d different values. So it can classically it could take on d different values 0 through d minus 1. Quantumly, it's in a superposition of all those d values. So now the energy penalty, so if there's an interaction between these two particles, the energy penalty is going to be given by a Hermitian matrix, right? Which so in other words, it's exactly as though these were classical d-state particles, in which case it would be some arbitrary function, but now it's a function in this space. So you actually pick a basis according to which you do the energy penalty. Yeah. These are the values of J. Yeah. Sorry, yeah. So there are plus minus ones, which are the values of J, and then there are also plus minus ones, which are the spins. Of course, these J's could have been other than plus minus 1 too, and maybe that would have been a better picture for me to draw. Yeah? Okay, so so that's the local interaction, right? It's described by a small Hermitian matrix. But if you want to say what's the energy penalty altogether, when you write the total Hamiltonian as h1 plus h2 plus so on up to hm, where these are the local interactions, what we are saying is, of course, h1, the Hamiltonian is, this term of the Hamiltonian is h1 tensored with the identity on all the rest, right? So h is going to be a very high dimensional matrix. It's a d to the n by d to the n matrix.